what we were able to do in the previous episodes is basically describe, the laws of the price processes, right? That's what we were able to do, but not the individual trajectories themselves, of prices, moving up and down, that actually carry the entropy production and the impact cost that we are, essentially describing distributionally, okay? So what we have to do is compute the quadratic variation or the path-dependent volatility, barrier statistics, all of these things, entropy balance, across every single realization or every single path. What we can do is use the Fokker-planck operator and lift it to something called a stochastic differential equation. All right, that's usually how we represent a Fokker-Planck operator, and we lift it to this SDE on the path, or let's say price path space. That's probably a better way to say it. On the price path space itself. And this lift here is not going to be very arbitrary because there's only one stochastic calculus. We have a selection of stochastic calculi to use. We have Ito's calculus, which depends on Ito's lemma. There's the Stratonovich, and there's also Malevin. Okay, and these three, there's only one of these will actually preserve the in the distributional sense of the symplectic structure of the underlying Hamiltonian phase space, or just the phase space that's volume preserving and the Seifert medium entropy simultaneously. So let's play around with this first. Let's say we have a price process that looks like this, and let's just say it's W sub s, and we want to integrate W sub s with respect to W sub s, and how we're measuring W sub s. In the Ito sense, okay, so let's say we have Ito's calculus. They invented this idea of integrating random processes from a left point evaluation. All right, so we're taking Riemann sums over the left point. And what this will do is say, because first of all, we don't know the future, right? That's essentially the assumption that we're making. So we'll want to take the limit of our partition as it goes to 0. For the increment of the process times, let's say I plus 1 minus I, and we basically make this telescoping sum, and there's an identity that can be derived in any stochastic calculus book. It says, well, we can take the idea that if we wanted the square of the Wiener increment with the minus the increment from the previous part of the process, this would be equivalent to Ti times the variation of the process plus the variation squared at that point. All right, and this will yield in a mean square limit, because we have to redefine the limit for random processes. This would give us that the integral itself will be 1/2 of the process varying with time, okay? And of course, that just seems like really simple, but we have to subtract off 1/2 t part of the term. And this extra term here that comes out of the Ito's formulation, it's basically the quadratic variation of the process. All right, so if I were to take, the covariance of the process with itself through time, it would be equivalent to t, right? And so the variation is equivalent to how long you're running your clock. Okay, and this explicit computation is required by the first problem. All right, here we say that the classical antiderivative is exactly the Itô integrals. It's different from the classical antiderivative by exactly half the quadratic variation. Okay? And the same correction appears in the general Itô formula. So let's just say for a general function, all right, a twice differentiable function, q, f of q, of, let's say, of the Stratonovich, or Stratonovich, whatever, I don't know how to say it, but of this Stratonovich process, lifted from its Fokker-Planck generator, the chain rule will acquire an extra second order term that, just looks something like this with the variance 1/2 times the variance with f. And this is our drift part of the stochastic differential equation. And the diffusion would be the derivative of the function itself scaled by the square root of the variance, okay, dw. Now this extra, and again, dw is the process itself, all right? So this extra term here, let's do it with red, why not? This extra term here is fictitious, all right? You have to understand that. This is not real. And it arises solely from just the idea of left point, of the left point discretization scheme that we use. It has no counterpart in the underlying actual deterministic Hamilton's equations. So if, let's say when this drift is inserted, let's insert this drift here, this extra drift, fictitious drift term, into some phase space 2 form. So let's say omega dq wedge dp. All right. We have this nice exterior form, and we can define a Lie derivative then along the vector field, and let's just call it the diffusion vector field, or you know what? I want to make a nice calligraphic L x diffusion. Okay. Acting with this Lie derivative on our exterior form here. And in this case, it's symplectic because it belongs to a Hamiltonian phase space that we talked about. Now, this would give us the diffusion along the vector field. I'm not going to prove this, but it will drag on this extra sigma, dq sigma dq wedge dp not being equivalent to 0. And so what's happening here, all you have to know from just a physics standpoint, let's go back over here. Boop. All you have to know is this, symplectic form not being equivalent to 0 when you act on it with when you act on it with a Lie derivative, the symplectic volume will leak, and so we get leaking volume, right? And what does that mean? That means that Liouville conservation is broken. So no Liouville conservation. And that just means that you cannot construct a Liouville measure over this Hamiltonian phase space. And what this is going to do is it's going to generate an unphysical contribution to entropy production. That is non-physical. All right? And this would be unrelated to any latent liquidity dissipation or anything like that. All right? So, and that's hence why whenever you do an Itô integral, formula or whatever, the price itself is decaying, right? And this is usually contextualized with, hey, there exists a numere, right, or a risk neutral measure that the physical price process is doing its thing, and really in the risk neutral sense, the path process is doing something like that, right? And it's like slowly decaying over time like that. Even though they're still the same, you just kind of put this fictitious drift here, okay? And it's a fictitious non-physical entropy production from the Itô integral, okay? Now, this is kind of important to recognize because guess what? The Stratonovich integral is actually physical. If we want to take the Stratonovich integral of some general function with respect to some general process, this would be defined as the limit of the partition going to 0, and it'd be a midpoint partition, okay? Instead, so it is teleological in a sense that it looks into the future, all right? F t times plus 1 over 2, okay? We're literally just taking the midpoint, and oh my god, I ran out of space, but this should be times w t. It's the same thing as previously. We're just taking the distance of that process itself, and this should be multiplied, there, okay? And it obeys the ordinary chain rule exactly. So you will exactly get the generator here of the SDE to be equivalent to this. And this just represents that we're doing it in the Stratonovich sense of just taking the midpoint. All right, that's all that little circle means. And if you substitute this correction into the Itô formula exactly, so if we substitute this into this, what one can have, I'm going to get rid of those circles, it's kind of messy, is that the Itô formula will cancel out this spurious drift. And remember how we defined the sigma. Sigma is what? Square root of 2d, right? If you did this, d being equivalent to k b dt market over gamma will hold, okay? And this would result, and I will leave this as an exercise to the video viewer. Usually, this is left as an exercise to the in the math books, they're usually like, this is left as an exercise to the reader. Well, I will leave this as an exercise to the video viewer to show that the resulting Stratonovich SDE will look like this. Therefore, it will conserve both the symplectic volume, okay? So in other words, the exterior derivative of the symplectic form will be equal to 0, and Cypher's decomposition, S total, which came from his paper that I linked in the Discord if you're interested, plus S the medium. This will also hold because it's a Stratonovich SDE, okay? And so the medium entropy is now exactly the work against the latent liquidity field with no fictitious contribution. And this is why we make it so that Stratonovich is mandatory, right? Because, first of all, why we choose Stratonovich? One, it reproduces the classical chain rule, all right? It gives us the classical chain rule. So two, it preserves symplectic form. And technically, since I'm going to call it Georgiev's phase space. Technically, Georgiev's phase space is weakly symplectic, but I just made it kind of like a deterministic version that's a little bit more of a order book empirical scaling. All right, so but it's still Georgiev's phase space because we're using the same conjugate variables. All right, and 3. I don't know why I changed the color. It makes the integral fluctuation theorem. Hold pathwise without any extra drift terms. All right, so that's why we need to choose Stratonovich over the rest of the calculi. All right, so hopefully that is enough justice, or hopefully that justifies enough for you, and you can go through and play around with these things. But because the drift coefficient, okay, let's say the drift coefficient itself may depend on time, right? This guy here. It could probably depend on time and the price space or whatever. Basically, it depends on the state, right? Okay. This process will naturally live on something we call a Riemannian manifold, whose metric is induced by vol. Okay. Now, the infinitesimal generator for the Stratonovich diffusion on this manifold is the Laplace-Beltrami operator. And what this looks like is if I have L to be equal to 1/2 square of the, or just variance, okay, 1/2 the variance with the Laplace-Beltrami operator here associated with some metric, let's say G, we're essentially making a coordinate, right, that depends, we're creating a metric that is induced by the volatility itself, and then we define the Laplace-Beltrami operator on that. And then we also need to have, this drift term dotted with a connection. All right? So that's the full Laplace-Beltrami operator over a Riemannian manifold, and this operator will replace flat space, the flat space second derivative, and automatically incorporate the curvature induced by state, again, this state-dependent volatility. And state-dependent volatility gives what? If you guys have ever seen Gatherell's surface here, his volatilities surfaces book, it's all about the entire book is on state-dependent volatility, right? And so, yeah, I mean, and the volatility surface itself is a Riemannian-like manifold, all right? It's usually assumed to be a smooth manifold in theory. And then, how to think about this, or how Gatherell thinks about this in his book, is that path-dependent volatility, barrier hitting times, all of these things are therefore intrinsic geometric they're intrinsic geometric quantities on the kinetic manifold, right? Rather than some ad hoc additions. Now, of course, there are more extrinsic or endogenous, factors that, or exogenous, endogenous. Those words, they mean the same shit. Okay, you kind of have to like do like a little dictionary, right, between different subjects, endogenous, intrinsic, whatever. There's really no difference if you're doing the same shit. Okay, but you can model the surface as well, like with external shocks and things. But at the end of the day, what's the point of what we're doing? Is we're trying to go from the order book observables to the surface itself. Okay, and trying to explain and do science. All right, with those things. So, at this dense bid-ask, when we have really dense bid-ask clusters, right? Just like, bid, right? And then ask, and then here's the mid price, all right? And then you have a market maker that's just like, liquidity sweeping through all these, okay? The clusters of the order book, right? And of course, remember, what did this give us? We invented a whole thing to describe the density, right, over all these Dirac deltas, and invented nuclear spaces, all these things. Okay, it all comes back. The reflecting Stratonovich SDE, these clusters, again, of the price process will be reflected based off of the internal geometry, right, of the volatility that's depending on the state. So, and of course, we would have some Riemann-metric, probably some kind of Fisher-like information metric or whatever. I don't know. Let's figure that out. But we essentially the reflected Stratonovich PDE, or sorry, SDE, would look like the normal process here with our diffusion and noise. But we also might want to tag on another part that reflects the local time process that is actually pushing the price away from the barrier, right? Let's say we have like a support resistance level or whatever that we observe and when we reconstruct the order book. The price gets pushed away from the barrier whenever it reaches zero occupation, right? So once there's no more and they get like sold off or whatever, there's nothing there anymore. And so the occupation measures the local time at a dense limit order book cluster. It could be given by something called the Ray-Knight theorem. And what this Ray-Knight theorem tells you is for a reflected Brownian motion, all right, so you have a boop, and then it's reflected over here, all right? For a reflected Brownian motion, starting at zero, the local time process, we call L of t at A, at level A, at that support resistance level, whatever, we have a law, okay, that comes from the Ray-Knight theorem. It says that if we were to integrate from 0 to t over the indicator of whenever, indicator function of whenever the q is equivalent to a, and we're integrating with respect to s, right, over that dummy variable, its occupation density will obey it's called a second order, occupation density, or just the density. It obeys a squared Bessel process of dimension 2. So the local time occupation will directly quantify, or the time that is occupied there at that level will directly quantify the time the time that the mid price spends pinned at each order book level, supplying the exact measure of Q depletion, or just the depletion of all of these orders that are there. Sorry, my iPad's about to die. and bid-ask bounce that enters the medium entropy here. And so I will also leave that as an exercise for you to play around with. But I've given you everything pretty much that you need to kind of put the pieces together. Okay? But the explicit Itô integral computation will reveal the quadratic variation correction. So we started off, again, with the Itô-Stratonovich conversion. It cancels out, this spurious drift precisely when the fluctuation and dissipation holds. The Laplace-Beltrami generator here, right? What this does it'll map the diffusion onto Riemannian manifold that basically is induced by state-dependent volatility in general. And this will reflect the SDE plus local time occupation as well. Local time occupation that you can play around with the Ray-Knight theorem. Gives you a law, essentially, of like how long it stays there. And enforce absorbing / reflecting barriers at dense limit order book clusters. So every path now carries a well-defined quadratic variation. Every path has a symplectic volume preserving flow because of Stratonovich. And what else? I mean, we have a manifold generator, right? And we have a time, basically we have a local time measure of barrier occupation, all right? Or of, support resistant level occupation. That's how you can think about it if you're a discretionary trader. Right? So all of these quantities remain tied to explicit limit order book observables. Again, what were our observables? Everything that you can see in a limit order book, we can try to play around with in the physics of it. But, spread, for example, just something like spread. Q size or volume. Even order flow rate, right? You can even think of it like as a magnetohydrodynamic system. Okay, I don't know. Like there's so much potential that we could explore, because what is magnetism in markets? And Georgiev also 2024, there's an open problem where he talks about the electromagnetic case of a Hamiltonian that basically would describe statistical arbitrage. Okay. Now I'm just gonna leave that there. There's high leverage when it comes to using physics to reason through the observables of the order book itself, of a limit order book specifically, and how we can just describe or transcribe distributions in the sense of like a discrete sum of Dirac measures and like this density, functional theoretic way, and lifting it to a causally consistent, geometrically invariant, stochastic process that's ready for things like gauge fields or symplectic invariance. Okay, so this is really the end, or this video is just really the end of like everything that's kind of that could be established, and the rest of these videos are going to be a little bit more speculative. Next episode I'll talk about gauge completion, and maybe some gauge theory. Okay, so see you guys next time. Bye-bye.